So we've seen how electrons take up certain shapes as they travel around a nucleus. The next factor to consider is their position in relation to the nucleus and in relation to any other electron. Now, as atoms increase the number of protons, so as we go from hydrogen to helium to lithium and onwards, we not only get more protons, but where the atom is neutral, we also get the same number of electrons. And where these electrons go is an important thing to be able to understand. The first rule is that we fill the lowest orbital first. So the very first orbital is called 1s. From that we learn the shape is spherical. We also learn that it's the closest orbital to the nucleus. The next orbital that gets filled is called 2s, again a spherical shape, but 2s has its electrons further away from the nucleus than 1s does. The next orbital is 2p, so a pendular shape, and 2p, remember p is larger on average than s, 2p is further away from the nucleus than 2s. 3s is further away than 2p, and this is also true as we extend out to 3p, 4s. Interestingly now, the next furthest one out is 3d. So the principle known as Aufbau principle breaks down here, but don't worry about it too much. As we talked about, the d orbitals and the f orbitals are somewhat of a preserve of inorganic chemistry. Organic chemists don't focus on it too much. It plays a role when we're thinking about sulfur and phosphorus and how it relates to carbon and molecules in that area. But for now, I don't want you to worry about that too much. The next rule we deal with is that the maximum number of electrons that we can introduce to any one orbital is 2. So we can have 1 electron present in an orbital, we can have 2 electrons present in an orbital, we cannot have 3 electrons present in an orbital. So the maximum number of electrons in one s orbital is 2. The maximum number of electrons in a 2s orbital is 2. And the maximum number of electrons in a 3s orbital is also 2. Now, the electrons are moving, and the direction they're moving in is also important. They can be approximately traveling clockwise or anti-clockwise. This is important when we think about magnetism being produced by the movement of the electron. If we look at the maximum 2 electrons present in an orbital, we can see that they are paired. 1 electron, if it's traveling clockwise, its partner must be traveling anti-clockwise. We use up arrows and down arrows to indicate these partners. Occasionally, this breaks down, but this isn't something to worry about at this point in time. Lastly, we need to think about the case where different orbitals have the same energy. These orbitals are described as being degenerate. This doesn't mean they've been down the pub at 2 o'clock in the morning and are blind drunk. It means that they have the same energy. For example, p orbitals very often have this situation. Now, where we have degenerate orbitals, orbitals of the same energy, they follow Hund's rule. And this is that we introduce 1 electron to one orbital, then we leave it partially filled. The next electron goes into another empty orbital. And if there's more, that remains unfilled. Next orbital that's empty gets filled. And we partially fill, that's to say we have 1 electron going into each orbital that is degenerate until they are all partially filled. And then we go back and we introduce a second electron into the first partially filled orbital.